Yeah, so when I was talking to David when he asked me to give a talk on GRBs, I thought about giving some highlights about GRBs, but really in recent days, I cannot stop but talking about GRB 221009A. So this is the brightest gamma ray burst ever detected. So in this picture, you can see a number of people, they are raising their hands up in the sky, maybe in joy about this burst, or maybe asking for having more bursts. But this is the group photo of the Fermi 10th International Fermi Symposium, which we held in Johannesburg from October 9 to 15. And this GRB 221009A happened on the 9th of October, the first day of the symposium. So obviously, a lot of people in that symposium, they were busy working on this burst while they're also trying to participate and listen to the talks. So as I said, this is a very interesting event detected by Swift BAT, also called the Swift J1913.1 plus 1946. It's detected also by Fermi Gamma Ray Burst Monitor. It's a relatively nearby burst. It's actually the second nearest long GRB. The nearest one is not really a full-blown long burst, but it was in 1998. This one is at ratio 0.151. So the left two cartoons, they show this Fermi lat detection. This is a 10-hour time-lapse image in gamma rays, and this was mentioned as the astronomy picture of the day. And the bottom one is the afterglow detected by Swift UVOT 10 hour after the burst. However, the most interesting detection from this burst is that in gamma rays, and as I mentioned, this is the brightest GRB ever detected. So there is a probability of having one of those is once in 100 years or longer. The isotropic gamma ray energy release is between 2 and 6, 10 to the power 54 erg. So that's huge. We never had this kind of energetic burst. And the Fermi lat detected greater than 100 MeV gamma rays until like 25 kilosecond. The highest energy photon detected was 99.3 GeV at 240 second post-trigger. However, the most interesting detection is by LASSO, a Chinese ground-based gamma ray observatory, and it detected 5,000 gamma rays between energy 0.5 to 18 TeV within 2 kiloseconds of the trigger. And this is the first GRB ever detected with energy, with gamma ray energy greater than 10 TeV. And not only that, there is a detector in Russia called Carpet 2, detected a 251 TeV gamma ray from this burst at 4,536 second post-trigger. With all these exciting results, there's a huge activity went on at the end of last year. So the NASA ADS is flooded with papers and GCNs. The last time when I was preparing this talk, I counted about 33 articles on ADS on this burst, and more than 120 GCNs and ATILs on this burst. So this is just a screenshot of the first dozen or so papers that I could fit on this slide. However, in my talk today, obviously biased, I'll talk about two papers. So one is this one, that's my own work with Justin Fink. It's about the possible evidence for Lorentz invariance violation in this gamma ray burst. And the second one, again, is also by me with Saikat Das. It's about ultra-high-energy cosmic ray signature in this GRB 221009A. The first paper is already published. It's in Abjad Letter, published earlier this year. You can find it. The second one is under review with the A&A letters. So let me then move on and talk about these two papers. The first one is the Lorentz invariance violation. Okay, so the Lorentz invariance violation comes from some expectation that the gravity is, the theory of gravity is quantized, the force of gravity is quantized, so there is some kind of description of the quantum nature of gravity at an energy scale called E quantum gravity. And people think that this is close to the Planck energy scale. Of course, the Planck energy scale is this one. Now, if we are close to this quantum gravity energy scale, then this Lorentz invariance is violated. Okay, so and the theory of special relativity is no longer true, and we have a speed of light that is no longer constant. And we can write it sort of in this photon dispersion relation in this quantum gravity model. So in the normal case, the right-hand side would be 0, but we have some terms here, and that depends on the some kind of weak perturbation model where this n is a number that comes from this perturbation theory, and this term, depending on whatever n you choose, you can have a different dispersion relation. And these plus minus signs refer to whether the photon speed is superluminal or plus is the subluminal and minus is the superluminal. But not only that, not only the photon speed is no longer constant, but also because of this, one of the fundamental processes in gamma ray astrophysics is this gamma-gamma going into electron-positron pairs. And the threshold energy for that process is also modified. So in the normal case, in the standard model case, this would be the threshold energy for gamma-gamma pair production would be this one term only, but because of this quantum gravity effect, there will be some additional term coming in for this threshold energy for electron-positron pair production. And this is written for the subluminal case, and if we have some n and E gamma not much less than E quantum gravity, then there will be an increase in the threshold energy for gamma-gamma going to E plus minus pairs. And that means the gamma rays, which are coming to us from a high redshift universe, like where the gamma ray bursts are, they are subject to electron-positron pair production with different background radiation field, okay? So, of course, if you have very, very energetic gamma rays, like PeV gamma rays, they can interact with the CMB. However, at lower energy, they interact with other background radiation field from infrared to UV. And these are commonly called the extragalactic background light. So if the threshold energy for gamma-gamma pair production is changed, that means the opacity of these gamma rays or gamma ray flux will be attenuated less severely from distant sources. So this is a model of what this extragalactic background light may look like, and its evolution with redshift from our model back in 2010. And this solid black line is the at redshift 0. At a higher redshift, it increases. Of course, it depends on the star formation rate and so on. So it increases and then it decreases again at very, very high redshift. So these gamma rays, the interaction, the change of the threshold for gamma-gamma interaction then affects the opacity in this way. So this is a plot from Beatty and Williams back in 2015. And this is the optical depth and the gamma ray energy, and for different redshifts. So if there is this violation of Lorentz invariance, then that is represented by the dashed curves over here, and that means they have reduced opacity for gamma rays compared to if there is no Lorentz invariance violation. And of course, I mean, it depends on the scale of the quantum gravity and also the number, what is the power in the perturbation theory that you take. So what we found is that for this GRB 221009A, so let me explain this curve. So this is a SED that we tried to build. This part from 0.1 GeV to 1 GeV, this is actually measured gamma ray flux detected by Fermi-Lat. And we extrapolated this to higher energy and folded in the gamma-gamma absorption. So this D and D, this is the intrinsic flux, so that represents this line over here, the extrapolated Fermi-Lat flux. And then you fold in the absorption due to this gamma-gamma pair production, and then you get the observed flux. So this would be representative of the observed flux. Now, the LASSO experiment detected one photon. We assume that there's one photon detected with 18 TeV energy, and from that you can calculate sort of like a Poisson lower limit on the flux. And the Carpet 2 detector detected one photon at 251 TeV. Again, from there you can calculate sort of like 95% confidence level Poisson lower limit on the flux. Now you can see that this detection, this Carpet 2 detection, cannot be explained by this flux after gamma-gamma attenuation. Okay, so the gamma-gamma attenuation would reduce the source flux to 0 at this energy. Thank you. But if we have Lorentz invariance violation, then we have this part of the spectrum over here, and that is really the effect of LIV. And then the flux actually goes down and goes up, and you can explain this Carpet 2 detection. We calculated what would be a limit on the gamma-gamma opacity from the intrinsic and observed flux, take the log of the ratio, and then you show that this upper limit on the gamma-gamma opacity for the two cases, n equal 1 and n equal 2 for this Carpet 2 detector detection, and you compute this limit on this quantum gravity energy scale, where the quantum gravity energy scale must be less than 49 times the Planck energy for n equal 1 and a million times smaller than the Planck energy for n equal 2. Okay, so I have much less time now, so let me move on to the second part, the ultra-high cosmic ray signature. So I'll skip some of these. The previous speaker has spoken about this model of gamma ray burst, prompt and afterglow emission. And what I mentioned here is that we then try to explain this LASSO observation of photons up to 18 TeV. So we considered in the afterglow model with the synchrotron self-Compton emission, and the ultra-high cosmic rays are also accelerated in this afterglow of the burst. However, any photon coming directly from the source would be severely attenuated in the EBL, as I mentioned earlier. At 18 TeV, the attenuation factor is like 10 to the minus 4.5. So what we do is we take these ultra-high cosmic rays, we assume that they escape from the jet, and they interact in the intergalactic medium with the CMB and with the EBL photons while they're coming along our line of sight. And if the magnetic field in the intergalactic medium is reasonably small, then all this emission can be aligned along the line of sight. Okay? And this actually avoids some of the EBL attenuation because the radiation is produced nearby compared to at the source. So, and also we try to explain the time delay of 2000 seconds for this ultra-high cosmic rays propagating in a magnetic field which is about 10 to the minus 5 nanogauss, and it's consistent with the constraints we have from other measurements, and we use a Monte Carlo propagation code for ultra-energy cosmic ray propagating and calculate the fraction of radiation coming in our direction, and we try to explain this emission. So this is the synchrotron self-Compton component, which is unable to account for this 10 TeV or 18 or greater than 10 TeV gamma ray flux detected from this burst. And this blue line is this ultra-energy cosmic ray induced cascade emission that may actually account for this greater than 10 TeV radiation. Okay, so if you care about the model parameters, here they are. I'll leave it there. So one interesting thing is that the total energy required in ultra-energy cosmic ray is quite reasonable. It's a fraction of the total energy released in gamma rays. So that's a good thing. And I leave you with this summary slide where this possible evidence for Lorentz invariance violation is quite intriguing. And we may have some evidence that ultra-energy cosmic rays can be accelerated in the gamma ray burst. Okay, thanks.